So shall I start?
Okay, go on.
Okay, so good afternoon, everyone, and thank you for being here today for the presentation of my PhD project, which is the impact of random events in social systems from individual sports to epidemics, which I conducted with Professor Alessandro Pluchino and Professor Andrea Rapisarda as my supervisors. So the general framework of this project is the study of social systems through the lens of complexity science. Indeed, complex systems have helped physicists to study a variety of social phenomena, from the most trivial ones, like the Mexican wave in a stadium, to the more critical, I would say, such as epidemic spreading all over the world, or even how the world itself can be thought as interconnected through social networks, for instance. But among the all possible phenomena one can study, the rich get richer mechanism, also called the Matthew effect, is very important because it's the mechanism that can explain the social and economic inequality in a social system. So not only from an economic point of view, but social inequality in general, because it explains how social advantages or disadvantages can beget further advantages or disadvantages. And it's also called the Matthew effect because of this quote from the Gospel of Matthew. But for physicists, the rich get richer mechanism is interesting because it can generate many nonlinear effects. And I'm going to talk about two different contexts where we can think of a rich get richer mechanism in place. On one hand, it lies at the origin of success in the sense that it amplifies the differences in the skills of individuals in a given context, determining who is more successful than others. On the other hand, maybe less evidently, it can also underlie an epidemic spreading in the sense that it amplifies the heterogeneous characteristics of a given complex social system, and it can become crucial if we want to assess the risk for that particular social system. Above all, what can trigger a rich get richer mechanism are random events. And this is the focus of my project. So let me start talking about success. Science of success has recently received lots of attention from scientific research because it can be studied in a variety of systems, through arts and show business, to music, to science itself, actually. And what appeals scientists is the mechanism behind success, this way where success can breed more and more success, and also how to connect the role that talent has or that the performance has in achieving success. What is being pointed out is that the role that the talent has is not enough to explain successful careers. So we miss another ingredient, which is luck or chance of random events in general. As it has been shown in this work, it's not enough if you are very talented to be successful. You also need to be very lucky. And with this idea in mind, what I wanted to study was how to quantify success and the role of random events in achieving success in sports. Why sports? Because we have a clear measure of performance in terms of very naively winning a match or a competition. And very often there is a nonlinear rewarding system after those performances as a consequence of these performances. And randomness can be very often explicitly involved in some sport rules. What I mean is that, for example, in case of a tie, randomness can be a factor to determine who wins. And in the end, sports can be seen as a classical example of a meritocratic environment. So if we want to rethink about this paradigm that we have of meritocracy, maybe we should start from this very controlled and simple, relatively simple example that sports can offer. In detail, I studied two different individual sports, fencing and tennis, that honestly share some similarities. In both sports, you can face an opponent in competitions that are structured as knockout, so direct elimination tournaments, and the goal is to rise in an official individual ranking. So allow me to start talking about what we did to study fencing. First of all, we looked into the literature and we found a very few attempts to study the role of success, how to quantify success in individual sports, like this one I'm showing here. In this work of Sokovitz et al., they studied 100-meter dash competitions, and they try to model the performance of the runners explicitly focusing on talent and chance as a linear combination of the two to represent performance. And they tried to reproduce the data they collected, trying to verify if this sport can be considered fully meritocratic, which means that the role of random events are very limited. So this parameter A, that is the weight of talent, should be equal to 1. But actually, they couldn't find A equal to 1 to reproduce the data. It's slightly, but significantly less than 1. What we did to analyze fencing was to abandon this idea to model the whole performance, which would be winning an entire match in terms of the linear combination of talent and chance. Instead, we moved to the microscopic level of how to model a single point, because every point can be affected by random fluctuations and by the talent of the players involved. So we use the same linear combination of talent and chance, but remember that.
Scusa Chiara, abbiamo perso la tua condivisione, vediamo te, non lo schermo.
Ok, io la vedevo condivisa, quindi lo rifaccio. Si vede ora?
Sì.
Sì, sì.
Okay, sorry for the inconvenience. As I was saying, in sports like fencing and tennis, there are always two opponents that face each other, right? So in this case, our single point PI, our single point is the PI for the opponent I and PJ for the opponent J. So if PI is greater than PJ, then I scores, and the other way around happens if J scores. Given the granularity of our model, we use an agent-based approach to try to reproduce the dynamics of fencing tournaments, where the only free global parameter is this A, so the weight of talent compared to chance. So we are at the level of how to score a single point in a match in fencing, where the two athletes can try to score at the same time, and whoever scores first gets the point. But you need several points, 15 in general, to win a match, and then you need to face several opponents and to win several matches if you want to eventually succeed in a competition. And we can reproduce this whole fencing dynamics by focusing on the microscopic level of how to score a single point. So what we did was to collect the international data for men and women in fencing competitions, and we struggled a lot to do that, but we managed to do that in the end, and so that we could fit our simulations to find out that the optimal weight for reproducing the data was A equal to 0.45. So the weight of talent is slightly less than chance, but we could fit for instance, the linear trend of points as a function of ranking, or testing other features of our data. For instance, we could verify that the top players, according to the ranking, do not very often reach the top positions in a given competition, as explained in the y-axis of this density plot. There is a non-zero probability of getting very low classifications for the top 16 players on the x-axis, which would be the ideal case of a perfect correspondence between ranking and competitions would be the dashed gray line in these plots, and this is quite well captured by our simulations. So now that we had this model to study fencing tournaments, we wanted to extend it to represent tennis, because in tennis we had the advantage of collecting more data more easily. But we needed to consider that while in fencing, the two athletes can try to score at the same time. So in the model, we could represent the random fluctuations of this point in a symmetrical way. What happens in tennis is that there are two different moments for the two players. So one is at service and the other at return. And we need to take into account of those structural bias in our model. So what we did was to start from what we consider to model a single point in fencing. And we had this split in serve and return to take into account the different contribution of chance, given that the probability of winning a point is different if the players are at serve or at return. Again, we used an agent-based approach to model tennis tournaments, and again, the only global parameter is the weight of time compared to chance, which is equal in the two cases. So if in fencing, after the calibration of our model, we found that this A was 0.45. In tennis, is actually even lower. One of the optimal value to reproduce our data is 0.20. So with this optimal simulation, we could test other features of the data that we had in tennis, because we could also have access to single match results other than competition results. So we could build networks like this, where there is a link from I to J if player with ranking J wins against player with ranking I. And we could verify that the simulation can capture the topological features of the network from the data, like the degree centrality and the eigenvector centrality I'm showing here. And we could test other things. For instance, one could ask who wins more often if we have players I and J that face each other, given the ranking position I and J. So we could build this triangular matrix whose elements A, I, J are the differences of wins of I against J and of J against I, normalized to the number of matches between the two. And in this visualization, the elements in red focus on the players that with a better ranking, they win more often, while the blue represents the opposite scenario. And we can see that in the panels on the left, the data in the simulation are in good agreement. And on the right in the zoom, we could also see that the simulation can capture quite well the trend on the data, where as we are approaching the diagonal of the matrix, we see that the blue elements increase, which means that the ranking positions are getting closer and the uncertainty of who is going to win increases. So the worst ranked players win more often. So after these two analyses with our agent-based approach, we found that the weight of talent in these two sports based on tournaments is quite low, actually, slightly less than chance in fencing, even lower in tennis. But what's going on? Does talent still count? Our answer is that our model reveals a paradoxical mechanism that that plays a role in very competitive environments, like in professional or very competitive sports, where the higher the level of competitiveness, then the more similar are the individual abilities of the athletes involved, and in the end, to discriminate between the two of them, even if they're both already very talented, their individual skills are not enough, so what becomes determinant are the random fluctuations to determine the match in the end. And if a single point can affect the whole match outcome, then different matches can weigh differently in the economy, not only of a single competition, but we could realize that there is a difference between winning the first round of a tournament or the semifinals or the final stages. But it could also affect different moments in the career of a player, because it can affect different competitions along that career. And maybe it can also affect the future development of the given career. So when I moved to Copenhagen to spend some research period abroad with the NERS group, we looked for possible indicators of future success if we look at the beginning of the professional career of tennis players. So what we did was to analyze tennis data to focus on the top players and see if there are any differences between top players and the other players, where top players are identified with their career peak in terms of the maximum amount of ranking points they had along their career. And we can see that there are some differences in not only in the evolution of their points in their ATP ranking, but there is also a difference if we look at the beginning of their career in terms of when they first appear in the official professional ranking. We can see that in the plot on the right that top players on average have more points from the beginning. So one hypothesis we wanted to test was if they have early access to more important tournaments. So we wanted a measure to distinguish which are the most important tournaments. So what we had was a sequence of tournaments that players can attend along their career. For sequences like this I'm showing in this slide. So let's imagine a player that starts with the US Open, then plays the Australian Open, then the Roland Garros, and then Wimbledon. We wanted to build a network where nodes are tournaments, and their links are created along that sequence I showed you before. So directly connected if they are directly one after another in the sequence, but also indirectly connected. For instance, the US Open is connected to Roland Garros because this imaginary player played first the US Open, then the Australian Open, and then Roland Garros, and so on and so forth. So we built this kind of network for all the tournaments we had in our data set to have their centrality in this network, a measure that not only captures their historical prestige in terms of the ATP rules themselves, as I'm showing here in the box plot on the top right, but it also includes the movements of the players along the whole system. With this, we wanted to look at the first 10 tournaments players attended at the beginning of their career. And we wanted to see if top players have early access to those tournaments. So if you look on the box plot on the left, we can see that actually there is no difference between top players and the others if we set the threshold, which is the black dashed line of high central tourneys. While if we consider the level of their first win, not of an entire tournament, an entire competition, but just of a match, then on the right in these box plots, we can see the top players actually merge. So if we consider, let's say, the combination of the right opportunity and a good performance, so when they had their first win in terms of network centrality, then we can have an indicator of future success for top players. So enough with the part that relates to success. Now I'm going to talk about epidemics. So we studied the first wave of COVID-19 in Italy because when it started, we could see a difference in the impact that COVID had in northern regions in Italy compared to the other regions in Italy. And at first sight, we thought about the steading of the outbreak that started in the northern of Italy, in the north of Italy. But actually, evidence showed that most likely the COVID-19 was already spread along the country, and there are many other works that went into such a direction. So when the national lockdown started, northern regions in Italy weren't the most affected in the sense that, or I should say, weren't the only one affected by COVID-19. So maybe there was something else related to their pre-existing characteristics that could explain such a discrepancy. So we wanted to build a risk index to differentiate between Italian regions. And we relied on Crichton's triangle to define risk in terms of three different components: hazard, exposure, and vulnerability, where hazard explains the potential of an event to cause damage. In epidemic spreading, it would be the probability of infection spreading, while exposure is the measure of the resource exposed to the potential damage. So in the epidemic context, it's represented by the population, while vulnerability is the propensity of such a resource to be damaged once exposed to the harmful event, which in the case of an epidemic, it can explain the differences of being infected and then being sick or even eventually die. So with this definition in mind, we built the risk index considering pre-existing factors that could explain the differences between Italian regions. So we could consider factors like this one on the top of the figure on the left as the hazard component, so factors that can explain the different rate of infection, or other factors like this in the middle of the plot that could affect the vulnerability of the people. And we used a multiplicative model to build this risk index to each Italian region to compare to the impact indicators of COVID-19. And we relied on total cases, number of deceased, and intensive care occupancies. So once we had this a priori risk index, because again, it's built on pre-existing conditions prior to the outbreak of COVID-19 in Italy, we could see that not only captures the general impact of COVID-19 in Italy, but it could also explain the impact of other viral infections that involve respiratory diseases like the seasonal flu. Of course, we tested that there is a correlation between the impact indicators of COVID-19 and the risk index. And we could also verify that, yes, according to the a priori risk index, northern Italy can be more affected by such an epidemic, because more than 70% of the a priori risk is concentrated in the northern regions of Italy. And that was also the case for the impact of COVID-19 during the first wave. We can also think of this risk index in terms of the two components, on one hand on hazard, and on the other hand the consequences, which is the combination of exposure and vulnerability, to directly visualize which are the regions that are more vulnerable and more exposed to such an harmful event. And we can also use this diagram to policy interventions that I'm not going to give you the details, but in terms of prevention, then we can know that we can intervene in the hazard component to reduce the hazard component, so the probability of infection, while if we want to intervene in terms of protection of the population, maybe we can try and reduce the vulnerability of the population. So to summarize, in this PhD project, I try to understand the role of random events that could affect two different contexts. I started talking about success in sports, and I tested how the influence of random events can start from the level of single points within a match, and then they can affect the whole evolution of the final rankings. Highlighting the presence of paradox of talent, which means that once again it's very unfair to apply the winner takes all logic when we think of our rewarding system. We move further to see that a combination of the right opportunity and a good performance can be crucial to get to the top in those sports. And when we change context, we see how the role of the heterogeneous features of a given complex system can be essential to correctly assess the risk in case of epidemic spreading. And here is a list of works that are already published or online or almost finished that came out after these 3 years of work. And with this, I think that I will end my talk. So thank you.